And I want to focus today just on one aspect of what we know about how the lung forms. I've been quite interested for a long time in how you get this incredible structure. This is just one of the fractal structures present in an adult human lung. This is the airway. There's parallel trees for the arterial structure and the venous structure, and there's tissues in between these trees. And you know, it starts as nothing. It starts as a little pouch poking out of the gut, and pretty soon it's got all of these useful parts. And you would think, oh well, it's scaled like a fractal. We know how to make fractals. We've got one just outside the door here. If you take a right out the door, it's actually strikingly similar, although clearly they were not constructed by the same technique, and they are adapted for very different purposes. Now, how the lung forms, you know, we'd like it to be very simple, but it's not. Is this showing well in this lighting? Okay, good. This angle is not so good from here. This is a 2D culture, so it's not completely accurate in representing what's going on in the natural lung morphogenesis, but you can pretty much see that it is starting out with a simpler geometry, and you get the branches forming at tips. So we call it tip splitting. And there's multiple tissues involved. It doesn't need to have a blood supply at this point. It doesn't need innervation. But it's growing, but it's also receiving some mechanical stimulation from itself and from its environment. And there's a lot of influences on the morphogenesis from the actions of growth, but the actions of living. I'm not going to get into the details of all of them given the time available, but essentially normal development, not just of lungs, but even limbs. Why do babies kick? Because they need to develop their musculoskeletal systems, and if they're impaired in their kicking, if there's nerve damage so that they can't kick, their musculoskeletal systems don't develop properly. And soft organs are very much the same in that if the lung as it's developing isn't allowed to breathe, to sigh, early on before there's a diaphragm, there are mechanical inputs from peristalsis, believe it or not, and we studied the mechanical inputs from peristalsis quite recently, but I won't talk about those today. What I want to focus on in terms of mechanical influences on the development of the lung is just simply what happens when you close off the trachea and its influences on development. Now, normally under development, the trachea is open, and the fetus later on, once it has a diaphragm, can engage in breathing motions, but experimentally, if you're growing one of these lungs in a dish, the trachea tends to pinch off, and the development is different in the case where it's pinched off in a wound healing response versus where you've kept it open with a tube to mimic better the natural possibilities of breathing, for example. And so let's focus on the influence of occlusion, the mechanical influence of occlusion on development in the lung. It's been known for quite some time, not just from this relatively recent study, but classical studies, from the 80s. Those of us from the 80s are classical now. In fetal sheep, they did surgical interventions and tied off one lung in the fetal sheep, and that lung that was tied off grew more robustly than its paired lung on the other side, which could breathe normally. So when you close off the trachea, you get more robust branching. So on the left, the control system, in a couple of days experimentally, you're getting this much more branching. It looks like it's roughly doubling in size. If you close off the trachea, you're not really getting more mass of the lung, not much more volume, but you're getting dramatically increased convolutions. You're getting more generations of branching with the same amount of tissue in the same amount of time. And why might that be? to the developmental biologist looking at it, well, you close it off and there's an increase in pressure and then you get more branching. To somebody who thinks about mechanics a lot, there's a few steps that have been omitted from that argument, and I want to know what those intermediate steps possibly could be in regulating the branching morphogenesis so that when you have the trachea closed off, you get more of it with the same amount of materials. How could that be? So we can speculate. I mean, it might be perfectly reasonable. If you are closing off the trachea, it makes sense. You would be possibly increasing the pressure inside because whatever is secreted can't drain. You don't think of the lung as a secretory organ, but it is. It's a glandular structure, just like your kidneys are glands. They're secreting urine. Your salivary glands are secreting saliva. Now everybody has to swallow, right? And your lungs are secreting all kinds of things. Think about it for a moment. Your lungs are not developing breathing air because there's no air in the developmental context. They're filled with liquid. The liquid that they're filled with is being secreted by the lungs themselves, and it exits the mouth and it becomes part of the amniotic fluid. The other part is urine. Nice to think about. That's what you're breathing before you have air to breathe. So if you're closing off the trachea, those secretions have nowhere to go. The pressure builds up. So, okay, let's look at what that does in terms of stretching the tissues. Does it make sense that closing off the trachea, increasing the pressure in the lumen, would be stretching the tissues enough to stimulate them developmentally? We can throw a model at that. I don't want to throw a complicated model at anything. I want to start simple in everything that I do. We can see the geometry of the lung at this stage of development. We can see the histology. It's really, really complicated. I want to start with something really, really simple that we can understand, a cylindrical pressure vessel. There's nothing to it. It's a standard engineering problem. I want to simplify the histology to just two tissues and a, whoops, where was I? To just two, whoop, I really went too far. I want to simplify it to just two tissues, a mesenchyme and an epithelium, filled with a fluid in the lumen, which is going to be under pressure. And I want to take a simple axisymmetric geometry, let the thing stretch, pressurize it with different pressures. We could examine the different stiffnesses of the tissues under real simple assumptions, but where are the stresses going to be and how much is this thing going to stretch, okay? It's a simple engineering question, and with the simplified geometry, we really can understand it completely. And so under different amounts of pressure, either no pressure because the trachea is open, no pressure, no observed stresses from the internal pressure. As the pressure is ramped up, we see the increased stresses in the inner tissues primarily. And then we can ask, how is that going to affect the branching? Well, where does the branching go on? The branching isn't from this inside layer. It's from the tips. Well, it's from perhaps the inside layer nearest the tip. But it's hard to see what's going on other than that the highest stresses are in the inner tissue. So we really need to go look at more of a native geometry. And so we had to segment from a 3D stack the different tissues to stick into our pressure vessel model and mesh it. And that, once that was set up, that's not a trivial task. Oh, does that show up at all? It's mostly supposed to be green. Is there a green channel? Let me, we are missing some of the video input. Well, there's supposed to be green under here. Well, there is supposed to be a geometry there. Not entirely. Is there a quick fix from the tech support people? No. I'll just talk you through it. Okay. So if the end is open, we are not seeing any gradients in stress. But as we increase the pressure, we're seeing essentially the same thing, that the highest pressures are in the inner tissue. And it's not really suggesting that there's anything special going on at the tips. So maybe we ought to look at specific surfaces within that 3D geometry, which really are not showing up.
Well, we can see it.
You can see
some green.
a little green. That's strange, but I'll take what I can get. I'll take what I can get. So on the business end is this epithelial surface. And as we increase the pressure from the left to the right, this inner surface of the epithelium, the primary stresses are in the stalks. The morphogenesis isn't really happening in the stalks, it's happening in the tips. So the logic that closing off the trachea increases the pressure and thereby stimulates more branching, there's a lot missing there because most of the stretch is in the stalks, which is not where the morphogenesis needs to be stimulated. We need to see it in the tips. Well, if you look at the next layer out, there are some stresses in the tips. But where they're in the tips, it's not in the, so if my head is a tip that's about to branch like Mickey Mouse here, the stresses, in order to be inducing extra branching, should be in the shoulders. But instead they're on the flat part on the side, which is not where we're seeing the branches. So it sounds good. You close it off, it pressurizes the lumen, and it stretches the tissues, and that stimulates branching. But it would be stimulating branching in the wrong place, at least according to this simple model. But what else could it be? If it's not stretching, what else could it possibly be? Well, maybe when you're closing off the trachea and blocking those secretions, you're also blocking transport of whatever was carried in those secretions, morphogens, biochemically active substances produced elsewhere in the tissue that then are not being carried in the fluid in the same manner that they were being carried in the natural system with the trachea open and the lumen contents free to flow. So let's throw another model at this. In this case, we're not so much pressurizing the lumen and looking for stretches, but we're closing off the flow and asking how that would alter the transport of substances being produced at this outer surface, which normally would diffuse and advect and bind to this surface, causing cell division. If the flow is free to flow, normally the fluid that would exit the lumen has to come from somewhere. It has to come from upstream in other tissues, coming from this tissue, which has to come from this tissue, which comes from outside. So if we're blocking off the flow, we're blocking off the transport of whatever has to be carried in that flow. So we have parameter estimates. We had to actually measure the viscosity of the fluid in the lumen of the embryonic lung, which is a very, very tiny thing. That was a cool thing to do. In 1D, you can get an analytical solution, which depends on the Peckway number. And we find that blocking off the trachea, well, if you think about it, blocking off the trachea is decreasing the fluid velocity and therefore decreasing the Peckway number. So diffusion is going to dominate as you're blocking off the trachea. And in 1D, you see that you're going to get an increase in the concentration of this hypothetical morphogen in the system. You're going to get an increase of concentration within the tissue as you're closing off the trachea. And you're also going to get a change in the shape of the profile within the tissue. But we're in 1D, so how would that really affect the morphogenesis? We got to look at 2D at least to see what's going on. And we do the same thing. We look at an axisymmetric model of this transport. And we see essentially the same thing that we see in 1D, where as you're decreasing the Peckway number because you're closing off the trachea, you get a higher concentration in the tissue, which is what is seen in vitro in these experimental cases. There is an actual chemical that we're thinking about. All of this is a simplified model. If we take this model into our 3D geometry, this is a slice through the 3D geometry, we see an increased concentration of this morphogen in the tissue. But I gotta say, you know, I look at this, how is this going to cause an increase in branching? How is this causing more cell division in the tips? I'm seeing an increase in this morphogen concentration in places where there isn't going to be branching. So this is still not a good model. It's not the stretching, it's not the concentration of this morphogen in the tissue. I'm not seeing anything that makes sense yet. But we got to look at one derivative, literally one derivative. What is the flux of this morphogen? It's not the concentration that matters. It's the flux of how much of this molecule is making it from the part of the lung that's generating it to the part that needs to receive it. And when we look at the flux, as we close off the trachea, it is redistributed to different places. It's really not obvious when you're looking at this concentration profile, so let's look at a plot of the flux to the different surfaces as we are ramping down that Peclet number. And much to our surprise, although the streamlines are the same, that makes sense, much to our surprise, as the Peclet number decreases, you get the same total flux. In this model, we're keeping the synthesis at that outer surface exactly the same. We're just changing the Peclet number. The total flux is the same, but very surprisingly to us, that flux gets redistributed to different places. And in particular, as you're closing off the trachea and reducing the Peclet number, you're getting that morphogen landing in more different places. There are more hot spots. And so if this morphogen is causing cell division, it's going to be causing it in more places when the trachea is closed off. And this was a very surprising result, both from the perspective of developmental biology, but even just, I think, from the perspective of fluid mechanics. I found it quite surprising. And I haven't found anybody who legitimately said, oh, that's obvious. Because I don't think it is necessarily obvious, and I would love to know if there's some kind of deep reason for it. So you can see it again when you look backwards. What we're seeing in 1D, you can't see a difference in the flux. In the axisymmetric plot, you can see a redistribution of where all of that flux is going. And you can definitely see it in the 3D, that you're getting more locations where the branching is going to happen. Another cute thing that happened is, well, I'll get to the cute thing. So this is just in summary. The case of closing off the trachea and getting more branching, it's a finer amount of detail because you're getting more of these hot spots. One cute thing that we saw is that we would occasionally see these triple hot spots, which I would suppose would lead to trifurcation. And our collaborator who's been working in this area in lung morphogenesis for quite some time said that they see it all the time, but it's against the anatomical dogma of the lung researchers. So he never reported it because he didn't want his papers to get hung up on a minor point. But we see trifurcation. So in summary, pressure vessel and stretches of the tissues, that seems quite plausible, but our assumptions in a basic model are not consistent with that hypothesis for increasing the branching by closing off the trachea. Looking at redistribution of the concentration of the hypothetical morphogens sounds plausible too, but there's not an immediate mechanism causing branching here and here and here versus here. Whereas if you're looking at the flux, that's the variable to look at. And that's where we really are seeing a plausible mechanism for increasing the branching in the lung. So I want to thank my students and collaborators. Most of this work was done by my postdoc, Uduak George, who is now at University of Georgia. And I thank you.
Time for a quick question or two.
Is there a relation with curvature, just the surface? Because it seemed to appear the higher flux and the higher curvature, which is typical in some branching in microbial filament too.
I think there is a strong relationship with the curvature, with the relative curvature of the outer surface and the inner surface. Because the signaling is coming from the outer surface with a low curvature, and it's being received by the inner surface, which has a higher curvature. So yeah, I think there really is a relationship, and we're working on that relationship right now.